All right, welcome. So in this video, I want to continue working with deterministic finite automatas and just really build up our intuition, building some DFAs for common languages to help us also understand where what kind of languages count as regular languages, those languages that can be accepted or recognized by a DFA. So let's start with this first one here. We're looking at a language that's going to be over the alphabet ABC now, slightly different than most of our examples so far, which has been 0, 1. This is just to remind us that we can be in a space where our alphabets change, okay? We're looking for all strings that start with AB and then also end with AB. So I'm going to start with a very simple state structure here where we get an A and then we get a B. And I haven't really said too much about this structure right now, but this might be the beginning. So let's maybe focus here on the starts with AB part. So if this is the starts with, we know we're starting at this state, so we get the AB. One thing we're going to want to think about here is what's going to happen if we don't get an A to start out. Well, if we don't start with an A, that means we don't start with an AB. And we probably should reject, and that means we should go to one of those states that I've been calling kind of a limbo state or a trap state, where once we're there, A, B, or C, we're out of luck. So that's if we get a B or a C from our first state, we've got the wrong symbol, we should go to the limbo state. Now if we get an A and then we get a B, we're good. We have more to do over here. But if we get an A and then we get something else like another A or a C, we're also in trouble. So we should go to our limbo state here. So I've kind of got that set up here. Now, once we've got started and we've got an A and a B, we're off to our races. We can now process some more of our string, but keeping in mind that we want to keep track of when we might end with an AB. So we want to stay in this state as long as we're currently in a state that's ended with AB, but we want to maybe leave this state if we're in any other case. So I'm going to start here by recognizing something very interesting here. If we just look at the string by itself, AB, we'll notice that this one starts with AB if we read it this way, but it also ends with AB if we look from the back to it. So this one technically counts as a string that we should accept. So that means that this state here should be an accept state, right? We know that we've processed our AB and we get here. Now what I'm saying is let's maybe reuse this accept state so that later on, let's say we get some other state here now. Well, I'm just going to imagine something else here. Now let's say we processed a C. And later on we might want to process an AB and return back to this state. But if we process a C, we know that we have not ended with AB. So we should go to a new state over here that does not have that is not an accept state. Now for instance, let's go back and check. We said that if we got a C, so maybe we got ABC, that doesn't work. That should be a no. But what about other ones like ABB or ABA? Those also seem to be not satisfying our pattern. So actually I feel like no matter what we get here, we should move off to this other state here. Okay, now I'm anticipating that we might want to keep track of one of these symbols. Now, which one of these symbols might we want to keep track of? If we got a B or a C, those are certainly bad, but if we got an A, let's look closer at this one here. If we had A, B, A, B, ooh, that other A, that might actually be the string that I'm looking for. So now we're kind of looking for a substring, which is something that we've looked at in a couple other examples, but it makes me think that maybe I was too eager when I put the A on there. I maybe thought, hey, if I get a B or C, I'm in one of these cases and I'm still looking for an A. But if I get an A, maybe I should move to a different state. And I'm going to go ahead and make that state here. If I get an A. And I'm also going to comment that if I came out of this state and I got an A, I should probably go here. Because what is this state supposed to represent for me? It's supposed to be if I can get a B after I get that A, I am now back into my state that tells me I should accept. So remember this string here, A, B, A, B. If we get this one, A, B, A, B, I end up back where I wanted to be. Okay. Notice I can also put some C's in there. A, B, C, C, A, B. I could go A, B, C. Uh-oh. I said I put two C's in there and I haven't finished this state yet. Well, I think that hints to me that what I want to do if I get a C is stay there. So A, B, C, C, A, B. I'm out to the accepting state. I started and ended with A, B. That looks like a good one. Okay. Well, notice maybe when I'm here, I also want to be there if I'm a B, right? I could put B's in there or C's in there. I can have any number of B's and C's in there. And then once I get the A, I want to get back out. Okay. There's another state that's unfinished here. Let's go back and review our rules for a deterministic finite automata. Part of what makes it a deterministic one, and we'll look at this in a future video, is that there's one output for every character in our alphabet. Okay, so for this state, we have A, B, C. 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 But for this state, we only put the B in, the one we wanted, and we didn't say what happens if we got an A or an A or a C. So what happens if we get an A? Well, remember, this state's detecting A's. So if we get an A, we should probably stay in the A state. If we get a B from the A state, we want to go to our accepting state. But if we get a C from the A state, so now let's think of this string, A, B, A, C, A, B. We got A, B, A. Now where should we go with the C so that we can detect the A, B? Well, I think the proper place for us to go is back to this state here, C, and now we've got A, B, C coming out of this state, and it looks like we've got a complete DFA. This was a little bit more complicated than I imagined when I made this, but it's because we're detecting both a substring to begin with and a substring to end with. So this is a very interesting, complex DFA, testing a little bit and hopefully building a little bit our intuition. Okay, let's look at another one here. This one, language 1, still working with A, B's, and C's. W contains at least one A, one B, and one C. So I'm going to think about this one in this way. I'm going to start with my start state. At the start state, we've only processed epsilon, which means we've processed no symbols. As the symbols come in, the next symbol might be an A, B, or C. As the symbols come in, I want to keep track of how many I've seen, which ones I've seen rather. If I see an A, I want to know, hey, I've seen an A. If I see a B, I want to know, hey, I've seen a B, and so on. And to do that, when we are thinking about what we want to remember or know or recall in our DFAs, it's the states that do that recollection for us. So over here, we can make 3 states, one for each of our 3 characters, and we might even give them names, A, B, and C, so that we can say that this is where I'm going to go if I have seen an A, this is where I'm going to go if I've seen a B, and this is where I'm going to go if I get a C. Now, what comes next is we could keep getting A's, so I want to keep that in mind for now. As long as I keep getting A's, I haven't learned any new information. I've detected A's, only A's, and I'll stay here. Same with this one, but for B's. As long I've seen a B, as long as I keep getting B's, nothing new is no new information. But what if I see something different? For instance, if I'm in this first state A and I see a B, I'm going to enter a new state. I'm going to put it here maybe strategically. If I get a B, maybe I'll call this state, maybe I should give it a little more space, AB. Because what it's going to be is it's going to keep in mind for me or remember for me when I've seen an A and a B. So I've seen A's to get here and I've seen a B to get here, and now I know that I've seen an A and a B. Okay. Well, notice there's another path that I could get here. Maybe I got a B and then I saw an A. So I could make it like this. Okay. Now you'll notice that this is only one of three possible cases I could be in after two characters, or at least two different characters. After one character, I'm going to be in one of three states, A, B, or C. But after two different characters, I'm going to be in either A, B, A, C, or B, C. And so I'm going to, again, kind of strategically draw these. I'm going to draw another one down here for B, C. Then I'll draw another right here for AC. And luckily, we're not quite done those states, but luckily we can see the finish line coming up. So I'm going to draw that state over here. We only need one more state over here. Maybe I'm going to draw it as a real big state. ABC, when I've seen all three characters. And maybe if we've developed our machine this far, we get a little eager and we think, oh, I'm done. I've got to the end state. That's my goal, so I must be done. But it's worthwhile to go back and double check like we did on our last machine. Do we have three transitions, A, B, C, exiting every state? So I just did that for the first state, and we saw that was true. Let's look at the next one. A, B, C. I didn't see it here because of the crossover lines. A, B, C. A, B, C. Okay, so we've got them all. But what about these states? We didn't do it. We only put the one we wanted, the C, outgoing. Okay, so what should we do here if we keep getting A's and B's? We should probably stay where we are. Remember, this is the A, B state. What happens here if we get an A and a C? We should stay in the AC state. And then same thing down here for our B's and C's. Now what about this final state? This is also a trap state or a limbo state, but it's actually a limbo state where we accept, so it's a good one. It's an accepting state, and so these ones I sort of differentiate from those trap states or limbo states like this one up above, where you're going to reject. This one is, hey, we've detected what we wanted and we're good to go. We don't need to do any other processing. We're just going to stay here and accept. So this is another interesting state. Look, we ended up having 8 different states, and it's interesting to note that those 8 states, as I mentioned, correspond to different cases. In the first case, when we had 0 symbols, we're at the epsilon case. Then we had A, B, or C. Then we could be A, B, A, C, or B, C. And then we just had A, B, C. And what you'll notice is these are all the possible subsets of the set A, B, C that you could have, and that's basically what we were trying to detect. As we were going, we were trying to detect which subset are we currently in. Have we detected A's? Have we detected A's and B's? Have we detected B's and C's? Which subset have we detected so far? Each one of these states corresponds to one of those subsets, and once we've detected the entire set, what we wanted, we can accept. So that's just an interesting way that our set theory can kind of inform or permutations, and some permutations and combinations as well, can really inform our design of these computational models. All right, let's keep moving on. So the next language here, we're going to move back to our binary alphabet here. We're going to now look at the length of W is divisible by 3. So let's remember that we've done some even odd stuff before, and even odd involved toggling back and forth between 2 different states, one that was for even and one that was for odd. Well, once we're doing other kinds of divisibility, like divisible by 3, we can just add in more states. So we can have here, since this is just saying the whole length, anytime we get a symbol, let's make this our start state so we can be clear. Anytime we get a symbol, we should move to the next state. So we're moving from maybe divisibility of 0 to divisibility of 1, or I should say 1 mod 3, or divisible. When we divide our length by 3, we would get a remainder of 1 to enter this state, a remainder of 2 to enter this state. So maybe I should write these down. 0, 1, 2. Okay. And then when we're doing divisible by 3, once you get to 3, you by mod 3, we're back to 0 again. Okay, so we get this toggle set up. Instead of it just being 2 settings, we got 3. Okay, and we sometimes call this a counter, because a state machine like this is central to the counter inside, say, your CPU that keeps track of what tick you are on, except that counter has more like 2 billion states. Sorry, actually 4 billion states if we have 2 to the 32, because 2 to the 32 is about 4 billion. Now, if you also had maybe a larger bit counter, say a 64-bit counter, then you'd have 2 to the 64 ticks. That's a really big number. I don't know what that one is, but it's incredibly big. So, you know, we probably don't need that many ticks. I'm not sure if our modern CPUs use that many ticks, but certainly you're going to see that. Now, why would I say we don't need that many? Well, when we get to the end, you can see in this state machine, we roll over to the other side, and that's what's going to happen here. We just go back to 0. So it doesn't really matter how big the counter is, as long as it's big enough to keep track of some of the times that we want to keep track of. With that said, we just built a very simple counter that counts up to 3 and keeps track of divisibility. One thing we haven't done yet is put any accepting states in this machine. So when should it be accepted? Well, we said we want the ones that are divisible by 3. Well, that's this state here. So that's our accept state, the one for 0. Now notice we could have also said, hey, what about the length is equivalent to 1 mod 3? Then it would have been this state that we wanted, or mod 2, or 2 mod 3 would be this state that we wanted. So it doesn't always have to be divisibility that we're interested in. It could be indivisibility or some remainder that we're interested in. And we saw that with the even odd, even being divisible by 2 and odd being indivisible by 2. Okay. Let's look at this next state here. This is an interesting one. What makes this one interesting is we've added an or. There's more than one condition that we might allow here. Or more than one thing that we're looking for, and that usually adds complexity to our machines. However, with ors and ands and so on, we'll see this a little bit later, we can somewhat, you know, as long as we have a finite number of ors or ands there, we can string as many as we want together to get another machine that will work. So we can merge machines together. Again, that's spoiler alert, look for the future. So what is this one looking for? Well, first it says it's got to start with a 0 or be divisible by 5. So what I'm going to do is I'm going to think conceptually for the moment. This doesn't always work, but it will for us right now. Because why is it going to work now? Well, starting with 0 and being divisible by 5 are pretty unrelated things. We can detect whether we start with 0 right away. So we did that sort of before. We had this sort of setup before where if we had a 0, we can go down one branch, and I'm going to think about what the machine might look like and maybe make some space over here. But if we get a 0 and we go down one branch, we can have a 1 and go down the other. That's detecting what we start with, okay? And then well, notice if we start with a 0, that's one of the things we want to detect. It's an OR. So once we know that, we can accept. We don't need to check any divisibility at all. So I'm going to make a little trap state up here. Hey, we started with 0. Good. We're done. But we started with 1. Now it's O. We know we don't start with a 0, so we need to keep moving, and we need to be thinking about being divisible by 5. Okay, so now what is that? Well, let's think about that counter we just designed up here for divisible by 3. Let's make one of these, but let's make it for divisible by 5. Another counter. So I use 5 states, and since it's the length, we don't care what symbol we're getting. We just want to transition to the next state. Now we've got 5 states here. Now we need to be really careful here. Which of these states is the state that is divisible by 5? Because up above in our divisible by 3 case, it was the starting state. Okay, so there's some instinct that makes us want to think that maybe it's this state here, right? That's the divisible by 5. But what we really need to realize or recognize is that to get to that state, we already processed one symbol, that first 1. And so this is actually equivalent to 1 mod 5 instead of equivalent to 0 mod 5 or divisible by 5. So if this is 1, maybe we'll put little symbols in here. 1, 2, 3, 4, 5, or 0. This is divisible by 5, so I made that one my accept state. Now what we need to recognize is we're actually missing out on exactly one string in this language by this machine, and that string is epsilon. Epsilon is such that the length of epsilon is 0, and that is equivalent to 0 mod 5, so it's divisible by 5. Okay, and so it should be accepted, but it is not currently because we did not make this an accept state. So epsilon does not start with 0. We shouldn't accept for that reason, but because it is divisible by 5, we should accept there. So that's a little special case. Maybe you missed that out if you were working on this as we're going and designed your own machine. So double check that. It's a good instinct. I usually do this. After I make a machine, try and think, hey, if I didn't already do it in the design of the machine, sometimes we do that above. We've done that in a few of our examples above. You think, hey, is epsilon something important? After I've designed my machine, I usually go back and say, wait a second, that's a special case often. Did I mess it up? Did I mess it up? Okay. All right, next one, has 4 zeros. I think this is going to be an easy one based on some of our prior videos. But this one, we're just counting zeros as we go. Okay. Has 4 zeros. That's a little ambiguous. Exactly 4 zeros, at most 4 zeros, at least 4 zeros. So that's ambiguous. But usually when we state it this way in natural language, we mean has 4 or more. So I'm going to say if you keep getting zeros, you're good to stay in this state, which is our accept state. Now, we almost kind of want to leave it like that. It seems like it only cares about zeros, but we need to remember that there are ones in our alphabet, so we just don't care about them. We're not tracking them. They belong in our language, so we'll keep them along, but we'll just ignore them. We won't make any state changes when we process them. All right, let's look at this one. It has 2 zeros and 2 ones. This is an interesting one. The ands make things a little bit harder, and we saw a good and one before when we said it had an A, a B, and a C, and this is kind of the same thing, 2 zeros and 2 ones. And we want to think, let's go back to that one, and let's think a little bit about how we handled that by keeping track of different states we were currently in. So we might start out in the state where we have epsilon. That's probably going to be our start state, where we haven't got any zeros or any ones. And then we could have 1 0. We could have 1 1. Once we've got 2 symbols in, we could have 2 zeros. We could have 0 1 or 1 0, which seem like the same state to me. That's one of each. And then 1 1. 2 ones. Okay. Now, remember, we could have, after that, we could have 3 zeros, but I'm not going to make an extra state for 3 zeros. I'm just going to, it's 2 or more. After I've got 2, I'm going to stop counting. Okay. But after I've got 2 zeros, I might get to 0, 0, 1. Or if I had 2 ones, I could get to 1, 1, 0. It looks like no matter which state I'm in here, because this is a 1, 1 and 1, 0 state, that if I get another 0, I'll end up over here. And if I get another 1, I'll end up over here. So those look like all the states that I need. And then once I'm here, again, if I get an extra 1 here, you know, we can see that finish line in our view, 0, 0, 1, 1. Okay, now I've drawn this as a plan, but I'm actually going to go ahead and do this now. With this structure, I can actually build my whole machine now. This is going to be my start state. Let's sort of see how it works. If I get a 0, I go here. If I get a 1, I go here. Okay. If I get another 0, I go here. But if I get a 1, I go here. If I got a 0 from there, I go here. And if I get a 1, I go here. It's a very straightforward way we designed this. It looks almost obvious how we're doing this. If we get a 1, we go here. We said in this state where we had 1 of each, if I get a 0, I go here. And if I get a 1, I go here. This one, if I get a 0, I go here. We've missed a few transitions so far, but let's just keep going with our plan. This one said if I get another 1 here, I go here. If I get another 0, I go here. And this was supposed to be our accept state. Okay. So now, to finish things off, we need to just double check where are those states that we've missed. Okay. 0, 1, 0, 1, 0, 1. This one doesn't have a 0. If I keep getting zeros here, I should stay here. 0, 1. If I keep getting 1s here, I should stay here. 0, 1. Okay, this one, same thing. We got a 1, we got a 0, but no 0 here. If I get a 0, we'll stay here. If I get a 1, I'll stay here. And finally, here, if I get a 0 or a 1, I'm just going to stay where I'm at. Okay, So this is a real interesting one. Again, using that same strategy we had above, we were able to design this really cool machine. And again, I left the labels right in there because once we started designing it in that way, I realized, hey, this is the structure of the machine that I want. All right, let's practice some substring ones now. So the next one is to remind ourselves how we do substring ones is we start by just making a state for each of the steps in our substring. So we go 1, and then I'm just reading the substring up above there, 1, 1, reading another 1, 1, and then 0, because that's the substring that we're looking for. If that was all the string we processed, this machine works, it gets us right there, but we now need to remember, okay, we need to worry about what happens if we get other symbols. Other symbols after we've processed it, we don't care, we stay right there. But other processes or other symbols we get while we're processing it might change what we're thinking of. So if we move this step here, when we get that first one, what do we do with zeros before we get our first one? Well, I guess we're just ignoring them. They're not part of our substring. Okay, we get the first one. We'll notice that if we get our next one, we keep moving down. But if we get a 0, oh no, we've upset our string, so it looks like we're going back to the beginning and starting over. 1, 1, 0, no, that's not our string. That's only part of it and not what we're looking for, so that brings us back. The 0 is not the beginning of our string, so we're back. And then again, 1, 1, 1. If I get a 0, I'm good. Here's the other interesting cool thing. If I keep getting 1s, I'm good. 1, 1, 1, 1, 1, 1, 1. We know as long as there's a 0 after that, we've got the string that we're looking for. So actually, we can keep getting 1s and just stay put in this state here. So there's this weird sort of transition here. Once you move past this point, there's no going back to the beginning. There's only going forward, but you still need to see that 1, 0 to make it to the next state. Okay, so that was not too hard, but the goal here was to try and use it to build up a strategy for doing the does not contain the substring. And it turns out that strategy is exactly the same. Let's just think about it right now. If we move forward here, we're going to start by trying to detect our symbols. 0, 0, reading the substring off, right? 1, and then we get to our final state, our trap state. We know it's a trap state because once we get there, we've detected our substring. But up above where we made it the accepting trap state, that's what we were looking for. Down below, this is our signal to not accept. So in fact, getting it maybe a little ahead of ourselves, as long as we haven't made it to that state, we want to accept. So there's that idea of flipping the accept and reject state. So we could design the whole machine like this and then flip them. Now I flipped them ahead of time because I haven't finished designing my machine yet, but I know that this is the state that detects, this is my trap limbo state where I want to reject, everything else is acceptable. So now let's think about the same choices up above here. Before I get that first 0, if I only get 1s, I'm just going to ignore them. If I get 1, 0 and then a 1, that's not what I'm looking for. So I was mistaken to move down this way. So I'm going to move back. If I got a 0 and then another 0, and then more zeros, I should probably stay there. Remember, same as that idea of lots of 1s up here. Okay. Now, if I get a 0 and a 0, and then, well, however many zeros, and then a 1, but then I get another 0, so let's be clear, I want 0, 0, 1. If I get another 1, I'm here, but if I get another 0, I'm actually good. It looked like I was getting that substring, but I didn't. Now it's bumped me back, and we need to remember that new 0 could be the beginning of the substring, so I don't want to go all the way back. I want to go to this state that detected my my 0. Now I didn't put my 0, 1 on here, but I should have. And now this is does not contain the substring 0, 0, 1, 1. Okay, let's just try that one more time. It's just a slightly longer substring, so it's not going to be too much more difficult. We're at does not contain, so that means these ones are all the accept states. Does not contain. This one is does contain, so we want to reject there. And now let's just think about our symbol processing. Before we get the first symbol that we're looking for, we're going to skip the other symbols, so we'll put the 0 there. Once we get the 1, if we get another 1, that could be the one we're looking for, so we'll just stay here as long as we keep getting 1s. then we get a 0. Now we got 1, 0, 1 instead of being what we're looking for, but that 1 could still be the beginning of the one we are looking for, so we won't go all the way back just to this state here. Now we've got 1, 0, 0. If we see that other 1, we're good. If we see the other 0, it actually messes us up. 1, 0, 0. Because of that 1, we can't just put more zeros in there. So actually getting that other 0 is going to reset us all the way back to the beginning. So now we've got 1, 0, 0, 1. Same idea. If we get a 0, we are reset all the way back to the beginning. And I'm going to draw that one over the top here, which is good. It's like we almost got there. 1, 0, 0, 1. If we had gotten the 1, we're in the reject state, but no, we got a 0. Aha, that resets us all the way back. We need to see another 1, 0, 0, 1, 0 before we can possibly reject ourselves. So that looks like we did that one. It's slightly more complicated, but I wouldn't say too much more. And I think you've probably noticed as you develop a few of these that the pattern is very similar. And so you do it a few times and you sort of build up that intuition. Okay, let's see if we can extend that a little bit. This one's trying to push our limits here. Contains the substring A, B, C at least twice. So I'm going to do once first. Now again, maybe I want to finish this submachine before I go and build up the second substring bit. So this is the first detection of the substring. So we're going to go ahead and skip any B's and C's before we get our first A. Once we see the A, if we get more A's, we're kind of lucky because it might be the beginning of our string. But if we got AC, for instance, we know that's not what we're looking for, so we would backtrack, looking for a new A to begin. But if we get a B, we're off to the races, so we should keep going. Now, if we got A, B, and we got another B, or another A for that matter, we should start over. Actually, I got that wrong. It's for another B, we should go there. If we got another A, we should go here because maybe that's the beginning of our ABC. Okay, but now let's see, we've got an A, B, and a C here. Again, if we got an A, B, and a C, we're off to the races. We're back to here, but now that means we've detected our substring once, and we need to go and find the second time. So once we're here and we've detected it once, we don't want to go back to the beginning and try and detect the first one again. So there is a sense that we might want to start fresh here. And I think I've got this idea where I might want to reproduce this whole machine I've just built over here. So I'm going to start with that structure. Then we want to think very carefully, what are the substructures that we want to build? Do I want to keep all these other transitions? Well, remember, if I got A, B, C, I don't want to backtrack any further. So if I keep getting B's and C's, it is like being in that start state up here. We want to stay here. Okay, we haven't seen the first A we want yet, but we're waiting for it. Okay, and when we do, we want to detect the second substring. Okay, the same thing here is I think the backtracking is going to be the same. If I see the A, we'll stay here if we get more A's. B's off to the races, but C is back to this state, not back all the way to the beginning. We're detecting the second substring. Okay, same thing with this state. If we need to backtrack, if we get another A, maybe we'll just backtrack one, but if we get a B, we're back to the beginning. And then finally, A, B, C, boom, that's what we're looking for. A, B, C, we're done. All right, now let's look at our final last one. Okay, W contains at least one A and an even number of C's. Now this one's starting to get us a little bit trickier. We've got an and, we've done a few ands in the past, and we've seen how we had to kind of weave the machine together. So I'm going to try and do this again. I'm going to keep track of two things as I'm going. I'm going to keep track of whether I've seen an A or not, and I'm going to keep track of the parity, the even or oddness of the number of C's that I've seen. So I'm going to just start thinking about, well, what's happening at the very beginning of my processing. At this point, I've seen an epsilon, remember. Okay. Now, if I've seen an epsilon, what are the states that might occur after I see my epsilon? Well, I might see an A, well, I'm drawing my machine with arrows over here. Maybe my machine will end up over here. I might see an A, or I might see a C, or I might see a B, and we're starting to see, so I'm going to build this in over here. This is my epsilon state. If I see a B, that doesn't help me with any of the things I'm detecting, the at least one A or the number of C's. And what I think what this is telling me is that in every state of the machine I'm going to build here, if I see a B, I'm going to ignore it. B's are pretty much, we might as well strip them out of our machine. And so for now, I'm pretty much going to ignore B's. So next up is, if I see an A, I want to move into a state or set of states that keeps track that I've seen at least one A. So I'm going to put I'm going to sort of indicate here, there's a column of states here that I'm going to be in here, that if I'm in this column, it means I've seen at least one A. And if I'm in this column over here, it means I've seen 0 A's. Okay, so 0 A's, 1 plus A's. Okay. All right, but I might also see a C. If I see a C, I want to move into, well, it says I want an even number of C's. So I want to move into a state here that's keeping track. And now I'm going to put a row here. That should be my odd state. Why odd? Because I've processed one C, so I must be in the odd state. This must be then my even C's state. Okay, and when I say state, I mean row of states or set of states. This one means an even number of C's, but this one also means an even number of C's. Okay, now let's go and think. So these are, I've finished processing this first state. I've at least created new states for my A's and my C's. But now let's think about this one. So in this one, I've seen at least one A. What happens if I see more A's? Well, this is 1 plus. So more A's do nothing. But also same with B's. Remember, B's I'm ignoring no matter what. But what if I see a C? Well, this is my even C's row. If I see a C, I should go to the odd C's. And that's down here. So I need a new state. C. We're going to move down here if I see a C. Okay, these are my odd states. Now notice, if I'm in the odd state and I see another C, I should move back to the even state. Notice when I did this, I stayed in my column. Why? Because when I process a C, it doesn't change how many A's I've seen, right? Going left to right, I'm keeping track of the A's. Going up and down, I'm keeping track of the C's, okay? Now again, if going left to right means I'm keeping track of the A's, if I'm in this state here, which is a odd number of C's state and 0 A's state, and I get an A, I should go to this state, which is an odd C state. It hasn't changed the number of C's, but it's now the 1 plus A state. And again, same idea we had over here. Once I'm over here, if I get an A, that doesn't, I'm in the pluses, and the B's are always the same. I didn't put my B loop over here, but the B's are always ignored. Okay, now let's just do a quick check. First state, A, B, C. This state, A, B, C. This state, A, B, C, and this state A, B, C. So we're done. This machine is done, except one thing we're missing is our except states. So where are we going to put those? So well, let's go back to our thing. So we can detect all the combinations of how many A's and even or odd numbers of C's. We've got the labels here. We just need to know which ones are except. It says contains at least one A and an even number of C's. So at 1 plus A's, we want this column, and an even number of C's, we want this row. So it looks like this state, because it's an and, we need both of those, is our except state. If it was an or, we would put one here and one here, because it would be either of those. Okay. If it was not and, okay, it would be all of these except for the one we have, or not or would be this one over here. So there are lots of different combinations we can get with different logical combinations here of ands, ors, and nots. But what what I want to sort of demonstrate here, and we saw it a little bit in the previous ones with ands as well, is you can make a two-dimensional structure. It's not always going to be two-dimensional, but if you only have two conjects, a thing and another one, you can kind of make a two-dimensional structure where maybe one dimension, the vertical dimension, is keeping track of one of your things that you need, one of the machines, and then the other structure is keeping track of so your horizontal dimension is keeping track of the other thing you're keeping track of. If you had three ands, you just need another dimension, and it's a little bit hard to draw that on a whiteboard like this, but you can still draw machines like that with crossing over lines, which is what we saw not with this machine, but this machine here, where we did, those were the other two AND machines. So this one has a hidden, oh no, there's the AND right there. Contains at least one A and at least one B and at least one C. So this was actually a 3 AND one, which is why we got those crossing over lines here. If you look at this structure, I'm pretty sure it's a cube. That's what we built here. You can kind of maybe make your eyes look at the node structure here and see it as a cube, the back face and the front face, okay? Or front face and back face, depending on how your brain oriented it. This one was two-dimensional, but that's because we only had two ands, two things in our and then this was two-dimensional because it only had two things in our and. So this idea we can extrapolate to build sort of these networks or lattices of states that can keep track of, like I said earlier, any finite number of properties that we can AND together, as long as each one of those properties is something that can be detected by a deterministic finite automata or as a regular language. A lot more on that coming. So thanks a lot for joining me in this exploration of deterministic finite automata, and we'll see you in that next video.